difference between the energy supplied to the control volume, there is also the difference between energy flowing in and energy flowing out. So if energy flowing in is more than the rate at which energy is flowing out, that will lead to accumulation of energy inside the control volume. Now, one thing which you have to notice is that the flow work has been included in the flow terms. So as a consequence, in these terms, we have the enthalpy, whereas in this term, we have the internal energy. Now, having derived this, let us do a few problems so that we are familiar how to use this before going over to the next topic. So the first problem deals with a nozzle. Steam at 0.6 megapascal 200 degrees centigrade enters an insulated nozzle with a velocity of 50 meters per second. It leaves at a pressure of 0.1 megapascal and a velocity of 600 meters per second. Determine the final temperature if the steam is superheated in the final state, and the quality if it is saturated. So we are doing an example. This is our nozzle. It is, I'm copying the diagram in a book. It assumes that the velocity is supersonic, which may or may not be true. So assuming it's supersonic, it draws the nozzle as converging diverging. So let's write down the statement of the first law. So this is a nozzle. Nothing is said about Q being supplied to the system. So I assume that this is equal to 0. Now work is done at the inlet, at the exit, but that is included in this term. So this would be supposing there were some veins inside it, and those veins are connected to a shaft. The shaft is connected to some device. Then there would be a work done in the control volume. Nothing of that sort is there inside a nozzle. So this I take to be 0. I have assumed here there was only one inlet, one exit. So therefore the um, summation term I have dropped while writing the equation. Now, assuming that this is operating at steady state, whatever the material properties at any point inside the control volume, so my control volume could be something like this. So at any point inside the control volume, the properties remain same. So if I integrate energy over the control volume, that does not change with time. So therefore, this also equals 0. Now I assume that the nozzle is placed horizontally. So therefore ZE and ZI are the same. Now for mass conservation, ME dot must be equal to MI dot. So if it were not, there would be accumulation of mass inside the control volume. Since it's at steady state, there's no accumulation of mass. Mass density also must remain constant at any point in the control volume with time. So then if I write down mass conservation law, then that would be uh, okay. So then for a system, mass must remain constant. Since this is at steady state, this must be 0. So this implies we have only one inlet and one exit. ME dot equal to MI dot. So therefore, if ME dot equal to MI dot and ZI equal to ZD, then this cancels with this.
Hello, sir.
Yes.
Sir, can you explain that why W dot CV is 0?
Okay. What is the work done by the material in the control volume? So then there are two components to it. One is what is done at the boundaries of the control volume. Now that has been included in this term H. Apart from that, work could be done by material in the control volume against something which is inside the control volume. So if I have a set of vanes, so if I have something like a turbine, it does work on the turbine blades. So that way energy is transferred to the turbine shaft. But for a nozzle, there is nothing like that inside. So within the control volume, it is not doing work against anything else. It is pressing against the wall with a certain pressure, but then the walls do not move. So the rate of work done would be forced into rate of displacement. There's no displacement perpendicular to the force. So therefore it does not do any, although it exerts pressure, it does not do any work on the walls. So therefore W dot CB is 0. Is it okay?
Okay, sir. Okay, sir.
Fine. Okay, so now that we know ME dot is equal to MI dot, so from this we would conclude that ME dot into HE plus V square by 2 is equal to MI dot into HI VI square by 2. But then we know ME dot is equal to MI dot. So therefore I can straight away write now HI is the enthalpy of steam at 0.6 megapascal 200 degrees centigrade.
Excuse me, sir.
Yes.
Sir, is it given in the question itself that it is steady state, steady flow?
Well, in fact, this is a thing which I have observed while setting questions for exams, that while when we set questions in the exams, we try as far as possible to specify everything very clearly. On the other hand, when we look at problems in the book, many things are sort of taken for granted. So in the book, since the discussion and the examples are given for steady state, when they give a problem, in many of those problems, it's not specifically stated, but the assumption is that unless stated otherwise, it is steady state. So it is not very clearly stated.
So by default, we have to take it steady state, steady flow.
Pardon?
By default, we have to take it as
By
steady
default,
state.
yes. Okay, we have done this before, but since enthalpy column we had not used in the past, let's do it once again. So 0.6 megapascal and 200 degrees centigrade. Now, looking at the pressure table, this is the saturated temperature base. This is the saturation line, base is pressure. So 0.6 megapascal, the saturation temperature is 158, and we are given the temperature of steam is 200 degrees, which means it is superheated. So let's go to the superheated part of the table. Point 0.6 megapascal. So scrolling down, let's come to 200. Now the columns were V, U, H and S. So S we still don't know what it is. H, this is the last but one column. That is what we need to see. So for 200 it is 2850.6. So H was in kilojoule per kg. Just confirming. So then we already know the values of VE and VI. VI is given as 50 meters per second, and VE, since it's a nozzle, it's being used to accelerate. VE is higher. It is 600 meters per second. So there is an increase in kinetic energy that must result in a decrease in enthalpy. So then HE is equal to HI. Now here you have to remember one thing. The kilojoule per kg, this is the unit for H, and for V it is meter square per second square. So how are the two related? Kilojoule per kg is equal to kilonewton meter per kg. Kilonewton is okay, it is 10 to the power 3 kg meter per second square meter by kg, because 1 Newton is 1 kg meter per second square. So 1 kilonewton is this. So 1 kilojoule per kg is not same as meter square per second square. So if you put in just numbers, you can't add them because the units are different. So then sorry.
Sir,
Yes.
sir, one question, one query, sir. Means for the problem practice from this part, sir, is FM white means good enough for solving the problems? Sir, it will be enough.
No, actually, I discussed the Reynolds transport theorem from FM White, but the problems which I am doing now are from Van Wylen and Sontag. Because
Sir,
these
from
are,
which? Uh, Sir, means from which part shall we practice the problems means, in Sontag?
okay. Van Wylen and Sontag, actually there are a large number of editions, so it depends on which edition you are following. But the chapters usually are uh, there is there are the preliminaries. After that, he discusses first law for a closed system and first law for an open system. So I think mainly first law for a closed system and first law for an open system. These are the two chapters from which you should solve the problems.
Okay, sir. Okay, sir.
So this evaluated turns out to be so this gives us the value of enthalpy at the exit. So coming back to our question, the question was determine the final temperature if the steam is superheated in the final state and the quality if it is saturated. So then the enthalpy increases with temperature. So then if the enthalpy which we have calculated is equal to the enthalpy of saturated steam. In that case, it is saturated steam. If the enthalpy is more, it means it is superheated steam. And if it is less, it means that it is not entirely in the vapor state. It is a liquid plus vapor. So once again, going back and comparing, this time we know the pressure is 0.15 megapascal. So let's go to the portion where it is 0.15. So this is the table for 0.15. At saturation, enthalpy is 2693.1 and our enthalpy is 2671. That means the enthalpy is less than the enthalpy of pure saturated steam, that is steam with quality 1. So if we heat it further, it would the enthalpy would increase, so it won't match the enthalpy which we have calculated. So therefore, it must be saturated steam. So then we have to look up the saturated steam properties. Saturated steam at 0.15. So then the enthalpy values are given here, 467.13 for liquid and 2693.1 for vapor. We are also given the enthalpy of vaporization. So that should make our task simpler. So then the for liquid it is 467.13 and the vaporization enthalpy is 2226.0. So then this would be equal to HF plus XE into so this gives us our answer that at the exit, steam is saturated vapor with quality 0.99. Let's do one more problem. This one didn't have a W.CV. That was the question which one of you asked. So let's do a problem which has a W.CV. The mass flow rate into a steam turbine is 1.5 kg per second and the heat transfer from the turbine is 8.5 kilowatt. The following data are known for steam entering and leaving the turbine. Inlet condition, pressure 2 megapascal, temperature 350 degrees, velocity 50 meters per second, elevation above reference plane 6 meters, exit conditions 0.1 megapascal pressure, quality 100%, velocity 100 meters per second, elevation above reference plane 3 meters. So we are given না আপনি কি সেলসম্যান? আমি একটা ক্লাসে আছি। আচ্ছা ঠিক আছে স্যার। ওকে হ্যাঁ okay. First thing is again assuming that it's operating in steady state, ME dot must be equal to MI dot, which is M dot, that is given as 1.5 kg per second, and at the inlet at the exit the value of acceleration due to gravity is also given here. So given a pressure of 2 megapascal and a temperature of 350 degrees centigrade, we again have to go and look up those tables. So I'm not doing that once again. I'm taking the final value. So we have done this exercise. You know how to do it. So given the pressure and the temperature, we can find out what is H this is saturated steam at 0.1 megapascal. Again, we can look up the properties of saturated steam, and from that we find it is
Excuse me, sir.
yes.
The, during examination, these enthalpy values will be given in the question itself, or we have to refer to that document?
Well, you'll have to use the table.
Yes.
In fact, yeah, I still haven't discussed about the exams because uh, thinking over it, with a class strength of 81, it is difficult to prevent people from using the book. So if I say that books are not allowed, the consequence would be that those who are honest would be at a disadvantage, because it would be difficult to prevent people from actually accessing the book, because online books would be available to you on your computer. So I think the best policy would be to make the exam officially open book and pose such a question that the answer will not be readily available. If you are able to solve it using the book, then it's fine. And actually that's realistic also, because later in real life, books will be available. You don't have to rely on memory. So then tables definitely will be permitted, and I've already provided you the tables. So you can all use those tables. Okay, so HI and HE, these are the values. Now, writing down the first law, Q dot CV is equal to, again assuming steady state, M dot so we need to evaluate Vi square by 2, V square by 2, GZI and GZE. HI and HE we have evaluated. So Vi square by 2 is equal to so again we have to divide by 1000 to express it as kilojoule per kg. So when we do that, it comes out to this. Velocity is twice, so energy will be 4 times. So this will be again this comes in meter square per second square. So again I have to divide by 1000. So one thing which you notice, HI, are of the order of few thousand kilojoules per kg. So the difference also is around um, uh, 500 kilojoules per kg. Whereas the kinetic energy and the potential energy are much smaller. So thermal energy typically has much larger magnitude than kinetic or potential energy when we are dealing with um, typical devices in thermal engineering. Now substituting the heat transfer from the turbine, so heat transfer is taken to be positive if it is to the system. This is from the system, so minus 8.5 kilowatt, that is kilojoule per second, is equal to 1.5 kg per second into the uh, enthalpy and other energies going out. So that would be 26 So given all the data, we observe that this is the rate at which uh, work output is obtained from the turbine. Now, if we look back, we were provided steam at 2 megapascal and 350 degrees centigrade. Now, depending on how much steam we are supplying and what is the diameter of the pipe, that will determine the velocity. Wherever we place the turbine, that will determine the height. Now, I expand it to 0.1 megapascal. 0.1 megapascal is roughly 1 atmosphere. So I have steam at high temperature, high pressure, and I expand it to atmospheric pressure. And then depending on the diameter of the pipe, that will determine what the velocity is. And the elevation is wherever I put the exit. Now the question comes, we are told in this problem that at the exit it is saturated steam. Now, can I arbitrarily specify whether it will be saturated or superheated, or is there some means of determining this? So in this problem, we have been provided pressure and temperature at inlet and pressure and quality at exit. This has been done because so far we have covered only the first law. So the first law only permits us to do an energy balance provided we are given the state at the inlet and at the exit. But then the first law is not all. The second law tells us, okay, if I assume here it was given that there is some heat loss from the turbine. Now, if I assume that it's an ideal situation, there's no heat loss, the steam expands adiabatically. When I say adiabatically, that means there's no heat transfer to the surroundings. In that case, if it were an ideal gas, if my pressure and temperature were given at the inlet and I knew the pressure at the exit, then from the relations for an adiabatic change, I could have calculated what is the temperature. So then the assumption that it's adiabatic should tell me what is the temperature if it is superheated or what is the quality if it is saturated. So we are still missing something. So whatever we are missing would actually come from the second law of thermodynamics. So in the next class, we'll take up the second law of thermodynamics. Okay, now okay.
Sir,
Huh.
are there any tutorial sheets for doing the questions?
Okay, so far I haven't given you any tutorial sheets. So as one of you asked, from where do I practice questions? So for practicing questions, you can practice questions from Van Wylen and Sontag, because that is from where I have taken the two problems.
Okay, sir.
So we can discuss this. Let me just download the attendance. Okay, so then since we have a little bit of time, let's discuss about the exams. So since there are three time slots given for the exams, we'll stick to our earlier decision that we'll have an exam next Friday. And according to the rules, the exam should be of at least 1 hour duration. So then we'll plan it accordingly. Then whatever we study this week will be the syllabus for the exam next Friday. So then we are going a little slow, but then we lost a bit of time. One was the first Wednesday we were told that Wednesday we should not take class because registration is not yet complete. So we lost one class over there. Then the holiday which was supposed to be on Thursday was shifted to Friday. So instead of losing a single lecture, we lost a double lecture. So we are going a little slow. Now I'm still following the guideline which seems to be this semester that don't take extra classes, stick to the timetable. So keeping that in mind, we'll have to see how what we can cover, what we cannot cover in fluid mechanics. And actually there is still quite a bit of time because it's the semester started in August, and the right now, so it was in middle of August when we started, and right now it's beginning of September. So if we require a little bit more of time for thermodynamics, it's probably okay. So apart from that, we'll have to have a few small quizzes because the rule says there's a weightage, and there's a guideline for weightage to the 3 exams, and what should be based on continuous evaluation. So the 3 exams, the weightage should not exceed 60%, and the continuous evaluation, it could be assignments, projects, class tests. So my experience says that assignments students always copy. So that is not a rational way. So the only rational way would be to have class tests, which means we lose further time. But keeping in mind the rules, it can't be helped. So we'll also have, so right now I've still not taken any small test. So because my first priority is completing the course material. So as the semester progresses, we'll have short class tests in between. And during the exam, be ready with paper and pen. So you'll be writing the exams like a conventional exam, and you'll also be instructed to upload a few answers at the end of the within the time limits. So if the exam is of 1 hour time limit, the final answers, which will be short, those will have to be uploaded within the 1 hour, and you'll get 10 minutes extra for scanning and emailing your full answers. So more of this we'll discuss on Friday during the break between the 2 lectures. But tentatively, whatever we cover this week will be the syllabus for the first class test of 1 hour duration, 1 or whatever we decide. I'll tell you in due course. It has to be at least 1 hour. So that test will be taken on next Friday. Any questions? Okay, then we'll stop here.